Hello everyone, in my today's talk, I will present a weight-adjusted discontinuous Galerkin method for wave propagation on moving curved meshes. In my research, I focus on high-order DG method, which shows several advantages for wave simulations. Firstly, the DG method can be applied on unstructured meshes, which provides high geometric flexibility. Secondly, as we all know that high-order methods can reduce numerical dissipation and dispersion over long time periods, as such high-order approximation can be easily achieved by DG methods. One only need to choose a high-order approximation space on a single element. Besides, the numerical solution will be more accurate per unknown as we increase the order of approximation. When paired with explicit time-stepping methods, DG schemes are readily parallelizable on GPUs. In practice, we may run into problems with moving domains, for example, wave scattering from vibrating boundaries, or as I present here, at the center of the domain, there is a rotating bar. Such moving domain problems require us to use some efficient way to capture the domain movement. And in this work, we will adopt the arbitrary Lagrangian-Eulerian method. For some of you may be not very familiar with the arbitrary Lagrangian-Eulerian method, I want to first present some background knowledge. The ARE method is a combination of purely Lagrangian and Eulerian method. In the Eulerian method, the mesh is fixed. So if the domain has some time-dependent deformations, then one needs a frequent remeshing technique to capture such deformations, which will be quite expensive. If we switch to the Lagrangian method, where mesh nodes are attached to the material, then we are able to handle time-dependent deformations relatively easy. However, if the deformation is too large, then we may have inverted elements and the mesh will be invalid. When we use the ARE method, mesh nodes can move arbitrarily. Because of such freedom offered by the ARE method, greater distortions can be handled compared with purely Lagrangian method and with higher resolution that can be offered by the purely Eulerian method. In this project, we need to transfer governing equations from a time-dependent physical domain to a stationary reference domain through an ARE transformation. The ARE transformation itself is very simple, which is just the chain rule. And for simplicity, we will restrict ourselves to 2D problems in this work. Now let me use the conservation law on a time-dependent physical domain to show you how to derive the corresponding ARE system. Using a chain rule, we are able to express derivatives on the physical domain as combinations of derivatives on the reference domain. Then we can multiply the equation by the Jacobian J between the reference domain and the physical domain, and cancel out all extra terms using metric identity and geometric conservation law. Eventually, we can obtain the ARE system, which consists of a conservation law on the reference domain and the geometric conservation law. An issue of DG method for moving curved meshes is energy stability. Now let me use a simplest constant solution to illustrate how we address the stability issue for mesh motion. By setting f equals 0 in the conservation law, we can immediately obtain the corresponding ARE system for the constant solution. We multiply the ARE system by test functions and integrate over elements, and then we can get the ARE DG formulation. To better prove the energy result, I will further rewrite this formulation into a skew-symmetric form by splitting the second term in the first equation. During integration by parts, we simply choose the central flux, which is the exterior value of the solution. So why this is a skew-symmetric formulation? Let's take a look at those red terms. I denote the sum by SUV. By assuming periodic or reflective boundary conditions, we can find that if we simply take V equals U, then in the summation, these two volume terms will cancel out, and the surface contribution from two neighboring elements will cancel out as well. So SUU equals 0, and it is a skew-symmetric term. One thing I want to point out is that non-evolving variables become Uj and J, which means that Uj is a polynomial of degree n, and J is also a polynomial of degree n. But the original variable is U. So at each time step, we need to compute U from Uj and J, and the way we compute U from Uj and J will directly influence energy result. And in the rest of my talk, I will use uj bar to denote the case when uj is treated as a degree n polynomial. Now let's talk about energy conservation. So if we compute u from uj bar and j using standard DG method, which means u is related to uj bar through the following relationship. In this case, u is computed by mj inverse times m times uj bar. So we will sum the ARE DG formulation over elements, and we can obtain the following equations. In this case, we will take the test function v equals to u, and w equals to 1/2 times projection of u squared. And we can simply ignore this skew-symmetric term as u because it is equal to 0. Now let's take a look at the second equation. So here j is a polynomial, so dj d tau is also a polynomial. And in the second term, since in our implementation we will first project jx hat t to a polynomial, so its divergence is also a polynomial. Because the L2 projection preserves polynomial moments, now we can simply get rid of the projection operators in the inner product. So the second equation becomes the following. And if we subtract it from the first equation, then we can immediately conclude that the ARE-DG scheme is energy conservative in the following sense. However, using standard DG method is not very practical in this case. Since now J, the Jacobian J is a time-dependent and spatially varying function. So one need to compute weighted mass matrices Mj at each time step and storing their inverses for each element, which will be very expensive. To address this issue, we will use the weight-adjusted approach to compute the solution U. The weight-adjusted approach is proposed by my PhD advisor, Dr. Jesse Chen, where the weighted mass matrix is approximated by an easily invertible and energy-stable weight-adjusted approximation, marked in red. And this approximation can be applied in a low storage and matrix-free manner, using quadrature-based interpolation and projection, L2 projection matrices, PQ and PQ, which are both reference operators, and they are the same for all elements. And for each element, we only need a vector to store the evaluations of Jacobian J at quadrature nodes. The weight-adjusted approach can significantly reduce the storage cost and speed up the implementation. And we can follow a similar step to obtain energy results when computing U using weight-adjusted approach. Now let me directly present you some theoretical results. So as I talked before, using a standard DG method, the change of energy is 0. And if we integrate over some time period, then we can get the second equation. However, if we switch to the weight-adjusted DG method, we don't have exact energy conservation. But the result is still good enough. We are able to show that the change of energy over a fixed time period can be bounded by some term that converges to 0 very fast. One thing I want to point out is that the energy in these two theorems are computed differently. But theoretically, we can show that these two energy measurements are actually equivalent, which means if one of them is bounded, the other will be bounded as well. Now, let's consider the acoustic wave equation. We will first rewrite the ARE system for the conservation law into matrix form. Here we will have two coefficient matrices consisting of geometric terms. Again, we adopt a skew-symmetric ARE DG formulation for the ARE system. I use the penalty flux for moving meshes, which can be regarded as an extension of the standard penalty flux on the fixed domain. With such penalty flux, we can show this skew-symmetric ARE DG formulation is consistent. And similarly, we are able to show stability results using standard DG and weight-adjusted DG respectively. The first theorem tells us if we use standard DG method to compute solutions, the change of energy is non-positive. And energy dissipation is aided through the penalty flux term. And in the second theorem, if we use a weight-adjusted approach, then change of energy is bounded by a term that converges to 0 plus a dissipative term. And in numerical experiment, we will see that this dissipative term will dominate the upper bound. Here I present some numerical results about energy conservation for 1D constant solutions. We can see that the convergence rates of energy variation for different orders are very close to the theoretical upper bound. And on the bottom, I also present the energy variation for standard DG method, which is very close to 0. This implies that the ARE DG scheme is energy conservative if we use standard DG method to compute a solution. For the 2D constant solution, we can observe similar convergence behavior. For the wave equation, so in the first experiment, we choose the central flux by setting penalty parameter to be 0. We again obtain the similar convergence behavior as constant solutions. But if we switch to the dissipative penalty flux, then we can see that the convergence using standard DG is very similar to that using weight-adjusted DG, which implies that the dissipative term will dominate the change in energy due to weight-adjusted approximation in the upper bound. In the next experiment, I tested the accuracy of ARE DG method for both central flux and penalty flux. In all cases, we can see that the convergence rates are very fast and close to the optimal convergence rate, which is order of H2n and a half. Here I show you two videos of wave propagation triggered by Gaussian pulses. The left one is on moving mesh, and the right one is on a stationary mesh. You can see these two numerical results are very similar, which indicates our method can handle mesh motion appropriately. In the end, I want to quickly summarize my today's talk. So in this talk, I present an ARE DG method to solve wave equations on moving meshes. The scheme can be proved to be energy stable up to a term that converges to 0 with sample rate as the optimal L2 error estimate. Finally, I want to thank NSF for supporting this project. Thank you.